Thank you, Chair, and good morning, everyone. I'm here to present some work that might help with certain problems that we're facing in total body PET. So first, in the simplest case, we can apply a radon transform to some image estimate that we have to get the model of the mean of the data that we have in tomographic reconstruction. And often we utilize iterative PET reconstruction, in my case, where we expand the radon transform to be a system matrix that closely models the geometry that we might have, and also include the real-world effects such as attenuation and normalization in our forward model. This way, using expectation maximization, we can get a better and better image estimate that matches the measured data more closely. However, when we're implementing our own research frameworks for PET reconstruction, getting these components that are specific to scanners with real data is quite difficult, especially normalization factors. These are quite tightly bound to the reconstruction software, which is proprietary, and the acquisitions. So this is something that we need to consider. Also, in iterative reconstruction, the biggest bottleneck is the system matrix itself. And this is defined by the total number of lines of response, which obviously grows as the scanner length increases. So, as we've had plenty of presentations yesterday and today, total body scanners are becoming the new state of the art. And they have a substantial increase in sensitivity, of course, because of their increase in axial length, which allows for effective low-dose imaging, but this sensitivity comes at a heavy computational cost. And as an illustrative example, let's compare two Siemens scanners that are identical apart from their length. The Vision 600, which is a standard PET scanner, and the Vision Quadra, which is a long axial field of view scanner. Just by increasing the length by 4 times, we have 16 times the LORs. So how can we do this? How can we deal with this extra computational cost? Well, the vendors, they use sonogram compression, where we use time-of-flight-aware view meshing to reduce the azimuthal view angles that we're dealing with, as well as reducing or including axial span compression, and also reducing the maximum ring difference in certain situations as well. Lastly, time-of-flight bin meshing is used to further reduce the number of bins that you use in the reconstruction procedure, which does indeed reduce the number of LORs that we have in our forward projection and back projections, but we still require a very powerful workstation with around 800 gigabytes of RAM, which is about £9,000 in today's economy. So it becomes quite difficult. So our solution, or one of our proposed solution, used LISMA data directly, which becomes quite useful because most of the time the number of events that we have are far fewer than the total LORs that the scanner might have, which makes it more efficient. So one method might be to generate a system matrix using each of the events that we acquire. But we still have the corrections as well as the full sensitivity image that we need to carry out a full reconstruction. And we can't get this directly using the acquired events themselves. So a solution proposed by Lawrence and Andrew a few years ago is use synthetic reconstruction, where we use a reference vendor reconstruction and forward project this using whatever system matrix that we may have, which will give us synthetic measurement data that embeds these corrections as well as the sensitivity image directly. With this, we can implement a synthetic MLEM reconstruction where we have these synthetic measurement values in lieu of real measurement values. So with this, we can benefit from a methodical generation of a system matrix using the acquired events directly. And as I mentioned before, we facilitate all of the corrections as well as the sensitivity image via the vendor reconstruction. And we can reconstruct a high quality image, sometimes faster, especially when we're using a fewer events or a smaller system matrix. This framework would allow us to have to implement new reconstruction methodology quite quickly and easily, such as changing the system model as well as using different reconstruction objectives as well. Lastly, we could reduce the number of events further by choosing a particular region of interest from this full total body scan that we may have, that we want to increase the quality rather than using the full volume, which could be quite time consuming. So to test this all out, we laid out the following experimental setup. Firstly, we have the vendor reconstructions obtained by E7 tools, and this uses 20 MLEM iterations, which is roughly equivalent to the clinical standard. This includes PSF modeling as well as without PSF modeling, which is the vendor's own models. But we chose to use the final non-PSF reconstruction as our reference image for the following reconstructions, as we wanted to implement our own PSF model to show that that we can change the reconstruction pathway even though we're using a reference without any of these present. Firstly, we wanted to implement a pure scanner-based synthetic reconstruction methodology or framework, which is what Lawrence and Andrew first implemented, where we generate our system matrix directly using the geometry rather than any of the acquired events. Using this, we can forward project a reference image to get synthetic values for that defined geometry, and then we can carry out some reconstruction. Here we've chosen 160 synthetic MLEM iterations with and without PSF model, and again, to emphasize, this is our own PSF model that we've implemented independent of the vendor. Lastly, we have our method, which is using the list mode data directly to generate a system matrix, and that way we can forward project this system forward project the reference image using the system matrix to get synthetic values for each list mode event of that particular acquisition. And as with before, we'd carry out some kind of reconstruction, also with and without PSF modeling. And to be specific about the actual experiments that we ran, for the pure scanner-based geometry, we chose the MMR as the biograph fusion MMR, the biographed MMR as our geometry, as this was just about enough with our computational limitations to carry out reconstructions, as well as the phantom that we chose fit nicely inside this geometry. We did 2D and fully 3D reconstructions, and to test the limit of our list mode derived reconstructions, we reduced the number of events that we acquired just randomly, as there is often lots of redundancies from a particular acquisition, to see how far we can go with reducing the size of our list mode derived system matrix. So to look at the how these actual this system matrix might look like, one way to see is the sensitivity images that we get. So from the vendor, we expect the full axial field of view, as well as the effects of attenuation normalization present in the sensitivity image. Compared with the MMR geometry, of course, the axial field of view is much shorter, but we don't need any corrections or components, as these are modeled with the vendor by forward projecting the vendor reconstruction. Lastly, we have our particular sensitivity image, and we can see there's an imprint of the actual acquisition, but this is expected as we're using the acquisition itself to generate our system matrix. And when we overlay the phantom over the sensitivity images, we can see that our method has a very data-specific sampling density, as you'd expect, with the way that we generate the system matrix. Okay, to look at some of the results, this is a background noise versus resolution trade-off of this real data, and we have the vendor reconstructions in orange, the MMR synthetic reconstructions in purple, and our reconstructions in green. We can see that the list mode data-derived synthetic methods generally converge to the reference, which is the final reconstruction on the vendor curve, the quickest, which show that the data-specific list mode data or data-specific system matrix facilitates in quicker reconstructions, as we are using the same number of MLEM iterations for both the MMR and the list mode derived reconstructions. And furthermore, we have a low bias variance trade-off or bias noise trade-off as well, compared to the vendor. This much of a gap was a bit of a surprise, as we're essentially modeling the same thing, but this is most likely due to the different projectors that we use compared to the vendor. And on the second set of curves that we show is with including the PSF model. And of course, we have a different PSF model compared to the vendor, and we achieve a better spatial resolution, but at the cost of amplifying high frequency noise. We chose a specific spatial frequency to compare our reconstructions, to compare the images, and we chose a 6mm spatial frequency, and those are the particular reconstructions that I'm about to show you, and here they are. So this is for a given spatial resolution, and we can see that generally the synthetic methods have lower noise, as the graphs indicated, for both with and without PSF modeling. It's difficult to see with the color map that I've chosen, but generally speaking, there's an increase in high resolution, high frequency noise, but with the PSF. But still, this is a model that we can change freely as well. Secondly, here we're showing a noise versus detectability trade-off, where we're measuring small lesion detectability, or in this case, with the phantoms, the small insert detectability. And again, we can generally see that both with and without PSF, we have high detectability for a given background variation. Okay, so this is an important metric that we wanted to emphasize, is that when we're doing these reconstructions from vendor reference, we can expect to see much faster reconstructions due to the smaller list mode derived system matrix that we have. So this is per iteration or per MLEM iteration, and compared to running a full quadro geometry in the sonogram domain, using list mode directly definitely increases speed. Secondly, the memory usage and the number of LORs that we use is also far fewer when compared against the vendor software, which is on the far left, versus our methods, which are on the right. Compared against a consumer GPU, that specifically the 3090 that I've used, we're well within the GPU limitation or maximum amount of RAM that we have for reconstruction. Lastly, I wanted to show some actual clinical reconstructions and the limits of the number of events that we need in this list mode data-derived system matrix for reconstruction. And we can see that even when using 1% of the total acquired events, we can achieve a similar spatial resolution to the actual vendor reconstructions. This is when we include a PSF model in the forward projection. And here it's a bit clearer to see some of the increase in high frequency noise due to the particular model that we've chosen. But again, this is something that is variable. We can choose whatever that we'd like. But the important thing is that we can change the reconstruction direction quite readily, which is especially clear with the large PSF kernel. So to conclude, we've introduced a novel paradigm, a research framework for PET reconstruction, where it is easy to implement, given that we have a vendor reconstruction as well as the acquired data. It requires no data corrections inherently due to use in the vendor reconstruction, where all of these things are embedded into the synthesized metadata. And as well as we can reduce the number of LORs in our system matrix by reducing the number of events, which can lead to faster reconstructions with higher quality. Our plans are to extend this in various different directions, especially in region of interest specific reconstructions, and increasing the resolution in particular regions that we might care about, as well as utilizing this extra time that we may have for more sophisticated system modeling, as well as extending the objective function for more for better reconstruction. Thank you for listening, and I welcome any questions.